How was your weekend? Mine too. It was good. Okay, today's review day. To answer all your confusions, right? Get confident on everything so you'll go into the test bravely and strongly, right? Hopefully nobody's going, test? What test? Well, we have a test Wednesday. Before I open it up for your questions, I would like to review, because I know it was the last thing we did, and I'm not naive enough to know that the last thing you talk about in a class on a Friday afternoon doesn't stick the best. So, that little vectors component stuff, it's not a big player right now. It will become in two-dimensional motion, but that vectors and components. If you have an x-y axis, like that, and let's say you're trying to pull a box here, you know, at the origin, and it's sliding along on the surface, but you pull it in that direction, the force of your pull. You guys know intuitively that it's not as effective pulling it up like that as it is if you pulled it horizontal. If any of you have ever tried to push or pull something, it's easier to push it in line with the way you want it to move. Yes, no? Give me some feedback. Yeah, okay. So the more up you pull it, the less effective you are. Take the extreme. This is always good in science. Thought problems. Think of the extremes. What if you pulled it perfectly straight up? Would the thing move sideways at all? No. Yeah, so the more up you get, the less that works. So what we do is figure out, if we wanted to know how this mass accelerated, we know that it's F over the mass. That's Newton's second law. But what force would we put in? It wouldn't be this one, because that's too much. It would be the component. And how you do that again is you drop a perpendicular to your axis, in this case the direction it's moving, or you want it to move. And this is a component of that. We could say it's the x component of the pull. And is that bigger or smaller than F pull? Smaller. Yeah, because you're only getting a portion of F pull in the x direction. So this, if you wanted to know the acceleration in the x direction, then you use the force in the x direction, and that would tell you how it accelerates. There's an example of how you could use it. You know, last time I just exposed you to it, but maybe didn't apply it. So we'll apply it a lot more in two-dimensional motion, projectile motion in Chapter 10. But they explain how to add vectors and this component stuff at the end of Chapter 5, so you might as well have it now. So when you're doing net forces, and I mentioned this, and you want to figure out how something's going to move, physics can help you. You just have to figure out how it's trying to move horizontally and work all those, and figure out how it's trying to move vertically and work all those. Because as soon as you get into 2 dimensions, you can't add like this to this directly. Or simply, anyway, I should say. That's how you add vectors. You break them into components and add the components up. Questions about that? Because I know I probably seemed zippy at the end of Friday. So. Now, I thought about it over the weekend. Nobody brought it up, but I bet some of you are thinking, how would you ever figure out what that is from that? Well, there's 2 things. If it's a right triangle like this, you can use Pythagorean theorem. The a squared plus b squared equals c squared. If this side is a, and this side is b, and this side is c, then a squared plus b squared equals c squared. You can figure it out. I'm not holding you to it mathematically as much. Who in here has had trigonometry? So the rest of you, don't spaz. I'm not asking you. but since you've had it, if this is an angle theta, then do you remember the cosine of theta is the opposite side, the adjacent side, A, adjacent, over the hypotenuse. So in our case, the pull in the x direction over the pull diagonally. So you could figure that out if you had to. For those of you that had trig, I thought I'd show you. The rest of you, don't spaz. I'm not asking you to do that. All right. What questions do you have about chapters 1 through 5? Open it up to you first. Yes? All the equations. I can try. For your reference, so I'm looking at chapter 1 here, and if you didn't notice, you go to the end of the chapter, they have a summary of the terms. While I'm on this one, for chapter 1, it was scientific method, hypothesis, scientific attitude, fact, law, theory. You should know what those are. But there weren't any equations. Or it would tell us. If you look at the end of chapter 2, that didn't have any equations either, but it had terms. Chapter 3 on linear motion. Now we had some equations, and there they are, summary of equations. So if I forget one right now, go check those out. I'll look at my notes, and let's see what I have. You go a certain distance, takes a certain amount of time. You know, it's 50 miles per hour. So that's speed. While your velocity then is the same thing. It just has a direction. Because it's a vector. And speed is a scalar, only magnitude. If you wanted, how would you measure instantaneous velocity? Say it again, I just couldn't hear you. Final minus initial what? All right, final velocity minus initial velocity. That would give us our instantaneous velocity. This by itself would just be the difference in velocity. Over time would give us something else. Acceleration. Yeah, actually it was plus because I messed up, didn't I? That would give your average velocity. So there's another one. In other words, let's say you start going 0 miles an hour, and then you end up going 50 miles an hour. Let's say you accelerate at a constant rate up there. You change your velocity at a constant rate. So I go from 0 to 50 throughout the trip. 0 at the beginning, 50 at the end. What's my average velocity throughout the trip? 25. That's how you could find that. So you would cover the same distance in the same amount of time if I had been going 25 miles an hour the whole time. That's how you can think of average velocity. Instantaneous velocity is a little harder. I asked that one first, so don't feel bad. So yes, go ahead. Yeah, instantaneous means it's at that very exact instant. That should be your clue on how we could find it. This finds the average over what? The whole trip, right? What if I wanted to find it right in the middle somewhere, or maybe right here? Use your reasoning skills. What if I actually wanted you to time it? You gave you a stopwatch and a meter stick or whatever, and I wanted you, you know, what do you think the instantaneous time velocity is right at this point, you know? You should have a clue that if this is our trip, it's closer to 50 than it is 0, but there we go. We could do that. That's a great idea. I didn't even think of that one this time. We could do the acceleration. So let's go ahead and write that definition down. It's the change in velocity with time. It's the rate of change of velocity. So just to note, that means your speed could be changing, because that means your velocity would be also. Or just your direction. Your speed could be constant, but you could be turning. That means your velocity is changing, and you'd be accelerating. Acceleration defines the rate at which your velocity changes. So yeah, if you knew it, like gravity we use a lot. The acceleration due to gravity is about 10 meters per second every second. So yeah, if we at that point, if it was 3 seconds later, I know I'm running this way. If we drop something 3 seconds later from rest, what's its velocity? It's instantaneous velocity at 3 seconds after free fall. 30, because it changed 10 in the first second, 10 more the second, and 10 more the third. So 3 times. Yeah, it'd be 30 seconds. That'd be a great way to find instantaneous velocity, if you knew the acceleration. What if you didn't know acceleration? Okay, I'm running across the whole trip. What if I could find the velocity right at this point? Would that more approximately tell me my velocity at the beginning of the trip? So it's like I'd use this initial velocity and maybe this final velocity instead of way over there. And then it'd give me an average for this part of it, but it's closer. So instantaneous is that. It's the same formulas. You just narrow it down. So you could look at a real small part, you know, from here to here. That'd be your instantaneous velocity in that region. Or look at it this way. Where's this one? Distance over time. Instead of looking at the whole distance, what if we just looked at the foot right here? How long did it take to go from here to here? That would give you your velocity right here, wouldn't it? So we say that's an instantaneous velocity. And the smaller you can make the intervals, the more instantaneous you are. So it's always an approximation, an instantaneous velocity. So your speedometer on your car, it's giving you an approximated instantaneous velocity, but you can trust it. Unless your car's whacked out. Then I guess you could try some story like that next time a cop pulls you over, right? Does that make sense? Okay. That's because we have 2 values. See, this might look like something new. You guys have been doing averages all your life, again, whether you realize it. Let's say you had 5 different values for the same thing. You tried to measure something and you did it 5 times. Or I picked 5 of you to measure the same thing. You might get different values. So we'd add up all 5 of them and divide by 5 because we had 5. And that would give us an average for the measurement, which would be more accurate in theory. That's what all this is doing. Take the beginning and the end one. There's only 2 of them. That's where the 2 comes from. I'm glad you asked that. All right, more formulas. We had, you want to know your final velocity at a certain point? Well, it depends on what you start at, if you're already going yay fast. And then, how fast you accelerate. Note that this is just that. So this is just combining common sense with our definition of acceleration. How will your velocity change? By the acceleration, by how long you accelerate. We just did that. We're 10 meters per second every second. We change 30 meters per second in 3 seconds. So that would tell you your change in velocity, and you add that to however fast you were going, and you'll now know how fast you're going afterwards. So we had that one. We had that one. We saw that it wasn't a linear relationship when the acceleration is constant. Remember our cart and the spots between the markers got further and further and further apart? Yeah, it's by a factor of 2. The position kept increasing, and it kept increasing not by the same amount, but more and more each second. That's what this embodies. And remember the cool things you can do? You know, you can spit your gum off the San Francisco Golden Gate Bridge, time how long it takes, 1001, 1002, 1003, splat. Boom, you know, approximate that as 10 meters per second squared, 3 seconds. You can even do that one in your head and know about how high up you are, or how deep your well is, or whatever the case it may be. You know, when your mortal enemy, you know, you guys are designing a superhero, right? Your mortal enemy pushes you out of the 10-story window, and there's nothing you can do. Well, you could count how long it takes to get to the bottom, and it gives you something to do as you're falling down, take your mind off the fact you'll probably die. You know? I thought it was funny. Okay, not the fact that you die. And, of course, we had Newton's second law. And if you have a bunch of forces, the net force is you just add up all the other forces that are acting on it. Anybody remembering any other one? I think that's it. We use this, like this one. If you want your weight, then you use your mass times the acceleration due to gravity. So it's mg. But it's really just Newton's second law applied to the force of Earth pulling on you. I think that should do you equation-wise. Gave us a good review of other stuff too. So that was just the first question. All right. What else? Yes? Absolutely. Help me out, class. What's a scalar? Yeah, it's only magnitude. It's just a number. What's a vector? Magnitude and direction, like Vector from Despicable Me, if you've seen that. I guess I should say, oh yeah. Who's seen it? At least don't think I'm a complete idiot up here. Okay. So that's the only difference. Vector includes a direction. Is force a vector? Is force a vector? Darn well better be, because we talk about direction with it all the time. It matters, the direction. So yes, force is an example of a vector. How about acceleration? 1 vote for scalar. 2 votes for scalar, 1 vote for vector. Does the direction matter? Does it matter which way you're accelerating? Oh, more yeses, so that leans towards vector. Yeah, it's even better. Acceleration is a change in velocity, and velocity is a vector, so acceleration is a vector. The easiest example, I think, is driving your car. You're going 50 miles an hour this way. I slam on the brakes. Which way there's a force now acting on me. Which way is that force? Yeah, that way. Which way am I moving? I'm still moving forward. So in layman's terms, we say I'm decelerating. It's slowing me down. It's changing my velocity by decreasing. In science, we'd say that's negative acceleration. Well, it depends on which way you're going. From your perspective, that would be negative because, to the left is generally negative. But, let's say I'm moving this way and I slam on the brakes. Now I'm accelerating that way. So anyway, direction is important for acceleration. It's an example of a vector. What's an example of a scalar? Other than speed. Good. Time. Mass. Yeah, who cares? I got my mass, but which way I direct it? Yeah, it's not important. Good. Distance. Now, that's a good question. If I use the word, I didn't get into it in this class, but scientists quibble over distance, position, and displacement. In layman's terms, we don't care, Distance is how far from one point to another. And it's the same distance whether you went from point A to B or B to A. So I would say distance is a scalar. Position, though, is a a vector. You can represent your position in three-dimensional space, and it matters which way you're pointing, You always need a reference point. Position relative to what? So position matters there. If some of you have heard of displacement, that's a vector because it matters which way you're going. I displaced a certain distance, but in that direction. It matters whether you went from A to B or B to A. It has that position. Reference. So, long story short, I would say distance is a scalar. We don't have to use them that much in this class to differentiate. So, next. What else has been bugging you? Homework problems, other things? Yes. You guys performed exactly like every other semester when I asked that question. In other words, it gave you guys the biggest headache. And you guys were no exception. So let's look at that one. I put that over here. It's the horse pulling the cart homework problem. You guys remember that one? So I use the same values here. So we have a cart and a horse. Yeah, forgive me. We'll give him some ears. All right. And then they drew all kinds of things on it. They had, for simplicity, I'm going to draw a free body diagram. Let's look at the cart. There's the cart. What forces are acting on the cart? You tell me. Gravity. Its weight. Next. The horse pulling the cart to the right. So, horse on cart. Friction, right. Okay, which way is the friction? Yeah, it's trying to oppose the direction of motion. So there's friction that the horse is trying to overcome. And technically, that's the ground on the cart, right? I could put that. Ground on cart. That's what, there's friction in the hubs and axle too. We lump it all in. And support force. See, look at you guys. Support, or normal force, same thing. Because it's normal, perpendicular to the surface. Others? All right, the first question asks, in the horizontal direction, how many forces are exerted on the cart? 2. There's your answer. And that's why. What confused some people is they saw all those other forces. But there's only 2 on the cart in the horizontal direction. There's 2 in the vertical direction on the cart also, but it didn't ask that. The other ones that throw people off is if the ground is pushing on the cart this way with friction, what's the cart doing to the ground? Yeah, it's pushing on the ground. But that's on the ground. The cart's trying to move the ground. That one's not on the cart. Likewise, another action-reaction pair. The horse is on the cart, pulling this way. You got that one. So what's the reaction? The cart back on the horse. Not friction. This is an action-reaction pair. This is an action-reaction pair. They have to be on opposite bodies, the pairs. But those aren't on the cart. Does that help for part A? Yeah. You were probably fine with that, and you want to just get the B, right? Well, then it said, what is the net horizontal force on the cart? We just add up those two forces. So the net force in the x direction on the cart is the force of the horse on the cart plus the friction going the other way. Now, we just said force is a vector. Those are in opposite directions. One of those has to have an opposite sign than the other. By convention, we generally say to the right is positive or up is positive. So this one would be positive the way I drew it, and that would be negative. So we'd have this one minus that one. Would give us our net force on the cart. And as long as the horse pulls with more force than friction, you can get it to move. Their terms were, so you can go back and check. They called this one P and this one little f. So P minus f, right, was the way that it was labeled in the thing. Does that make sense now? Yeah. Other concerns?
So the one that confused me was the action-reaction pair on the guy that was standing there. Like, I'm not trying to understand the difference between force and then action.
Like when I stand on the scale, that type of thing?
Well, he was just standing on the ground.
Yeah, yeah. Let's do those again, because I've done it twice and it's confusing, see? All right, what are the forces acting on a person just standing there? Support and gravity. Normal force. Wait. Are those on the person? Yes. So those can't be an action-reaction pair. All right, what's the reaction to this force? What causes it? That always helps you. What's causing this force? Gravity. The earth pulling on the person. So what's the pair? The person pulling back on the earth. Yeah. Back on earth. Or up. Whoops. On earth. That's the pair there. Notice that one's on the earth, not the person. What's the reaction to this one? The ground is supporting the person and pushing up on the person. So what's the pair with that? Pushing on the ground. Yeah, you put it down here. You're pushing on the ground to that normal force. Down on ground. Again, notice that's not on the person. Now, these are, if you're just standing there, perpendicular to the surface and not moving, these are equal. And that's what throws a lot of people off. Because you get on a scale, and what's it measure? You push down on the scale pushes back. If you're not moving, these are equal. That's what a scale measures, is that support force. We have that force because the earth pulled down on us, but it's not the reaction. Earth pulls on us, so I pull up on it. If I happen to be running into the ground now keeps me from going down any further, supports me. So I'm obviously exerting a force on the ground. And that's the action-reaction pair for there. Does that help? No? Okay.
So there is an action-reaction pair. There are two action-reaction pairs.
There are two pairs.
But the earth pulling down on the person.
Earth pulls down on the person.
Right. And what was the FN again?
Normal or support force.
So that's the support force. And that goes the
Yes, and your tip-off is they're both on the person, the same body, and an action-reaction pair can't be on the same object. The underlying thing of all this is Newton's third law. All forces come in pairs. You can't have a force by itself. There's always some reaction to it. Who's the action? Who's the reaction? Yeah, whatever. But they're on opposite bodies. So if the Earth's pulling on me, then I'm pulling on the Earth. If I'm running into the ground, then it's pushing back on me. Or if it's holding me up, then I'm pushing on it. These two do not affect my motion because they're not on me. But these two are. So we put them together in a free body diagram, force body diagram, sum up the forces, and that could tell you your motion through Newton's second law, how that your mass is going to accelerate, if at all.
So if both forces are acting on the same object, there's not an action-reaction.
Correct. If both forces act on the same object, those can't be a pair. Another example, let's see, hone it in. I hit your face. Psh. What's the pair? Yeah, my hand on face. Face pushes back on hand. It hurts. Yeah. Another one. Who likes to golf? Not as many golfers. Huh? Baseball? Less there. Okay, well. All right. You hit the golf ball. Whoopsh. Club on ball. Ball on club. They feel the exact same force. Who gets accelerated more? The ball. Why? Has less mass. That's one reason they got those bigger heads. You know, now they look funny. In my day, they were more mass. You can get a greater change in velocity. So it also increases the sweet spot, so you're more leeway for messing up. And that's probably the real reason. But yeah, you just make something real massive. That helps. Good. Anything else? Yes? The ball changes shape. For what? What? Oh, when a club hits it. Is that in 1 through 5? I remember that in a later chapter. Well, if you find it, I can be more specific to you. But what I'm thinking is, acceleration is, simply put, a change in velocity. So if you can get something to go from 0 up to something else, you've accelerated it. Whether it deforms or not to make that possible doesn't affect the acceleration. It's just how much it changes. Can you get something to accelerate more by having it deform? Probably. You know, it's like hitting something hard versus something squishy. You could do the same thing and it would have a different effect on it. That starts getting into the amount it smushes and the time it takes during that collision. And that's when we get into impulse and momentum. And you can change how much force is acting on something by changing that, adjusting that. And if you adjust that, you adjust the force acting on it. From Newton's second law, you can then change the acceleration on it. But acceleration is still just that change in velocity. Does that work for now? Well, you're reading ahead. That's awesome. That's what's next after the test. Anything else bugging you? So, does the homework make sense now, where you guys have gone through them? How many have looked at answer keys? I'm curious. That's par for the course. I friendly remind you that, yes, I know, and that's why I use WebAssign, is you know what the correct answers are. You should by the time you finish the assignment. But many of them, not all, but many of them have an extra sentence or three of mine explaining more about it. So if it's confusing to you or you think you don't understand it as well, you can go read that. It might give you more than you didn't realize. No, we do everything on WebAssign. The assignments are on WebAssign. WebAssign grades them. They're posted. You can always see your grades there. Someone did ask, Canvas grades nothing. I have decided for your convenience to periodically, it's not automatic, upload your scores from WebAssign on Canvas so you can see everything. Because WebAssign doesn't weight your grades like I do. Canvas can let me, because you're like the pre-lecture questions are 5% of your overall grade. I can't show that in WebAssign. So your overall grade in WebAssign is bogus. Don't trust your overall grade in WebAssign. So I put them in Canvas so you can see that. But that's all I'm using it for. That and to get us registered with clickers so we can integrate you. If you go back to past assignments, you can click on any of them. And when you open it, there's a button. And there's a big box, too, that warns you. Here's the answer key. Realize that once you click on this, you can see the answers. Be sure you've turned everything in, or I won't grant you an extension type of thing, because then you've seen the answers. But let's ask you a few clicker questions then on Chapter 5, the most recent stuff, and see how you feel there. What? Am I posting them? No, especially since they're recorded. I mean, the scores, yes. The questions themselves, no. We'll see how this can jog our memory with some stuff. The first one should be, I hope, is easy now. I'll go ahead and open polling for those that are ready. And while you're logging in, I'll look and see if there's something else mission critical I should tell you. I do want to tell you, I'll remind you Wednesday, but I never know how to say this without sounding bad, so I'll just say it and then clarify it. On the test, ask me if you have questions. I would rather you miss the question because of you don't know the physics, that's where it sounds bad, than because you don't understand the question, or what I mean, or what I'm asking, or the English. So if you have a question on the test, it's okay, you can ask me. I want you to at least understand what I'm asking. Then I can gauge whether or not you know the physics. Yes, I want you to get the physics right too, but I don't want you to miss a question just because you're confused about something. It requires a number 2 pencil, so if you have one, bring it, but we'll provide some. Again, I provide the bubble sheet. It's multiple choice, same format you've been seeing. You can have your cheat sheet and a calculator. I'll just ask that you don't sit next to someone else. We'll just put a chair in between everybody, and then I'll watch around and make sure you're not cheating. All right, looks like most people have answered. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 93%. 2 forces. Very good. I won't lie, I'm a little concerned the very few of you that missed that. Can I help? So yeah, all forces come in pairs. For every action, there's an equal and opposite reaction. So it has to be at least 2. See if you can get this one then. I picked these before I decide what I'll be telling you before I ask them, so it should be more obvious now after what we just discussed. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Hey, we got 3 more people. All right. Overwhelming majority, all. Very good. Opposite in direction, equal in magnitude, and they have to occur at the same time. So it's not like I push you, and then all of a sudden, 30 seconds later, you push back. No, it has to be at the same time. That'll come into be more important as we get into momentum and impulse with collisions. All right, try that one. So I just smushed 2 carts together, smushing a spring in between them. If I let go, what happens? Must have been a reaction force, too. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hey, we gained even another person. This is great. They will be equal. How do you know they're equal? Because they're the same mass. It said they were identical. If they were different masses, the accelerations would be different, right? And you know the one with more mass would have less acceleration. That's Newton's second law. Questions? Okay. We did this demo. Ten. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Well, at the lowest percentage, still 83, we got ejected air. So talk to me. The other answers, what were you thinking? I'll help you. Yes? Ah, which is why I asked this. Good, it worked. We're helping clarify some. So if the balloon is pushing air out that way, then it runs into surrounding air. And that surrounding air is what pushes it. What does the surrounding air act on? The other air. So it's pushing on the ejected air. So it's going to affect the ejected air's motion. What's pushing on the balloon? The ejected air only. So you don't need, this works in space. You could take an air-filled balloon in space, despite all the other problems with that, I know, and eject the air. If the balloon pushes the air out, Newton's third law says it's the exact same force, but opposite direction, back on the balloon. The ejected air is pushing back on the balloon, and that's what propels it. You don't have to put it against a wall. It's not the wall that pushes it. It's not the surrounding air. Balloon on air, air back on balloon. Even if there was no air in this room, just in the balloon. Does that help? And that's an action-reaction pair. There'd be another pair then if the ejected air runs into the surrounding air pushes back on the ejected air. There's a pair, but again on opposite bodies. One more. Come on. I'm optimistic. Here's a truck and here's a mosquito. Wham. They're moving. They could be speeding up, slowing down, or not. Wouldn't matter for this. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ooh, overwhelming D. So Newton's third law says, hey, they're going to feel the exact same force. But because the mosquito's mass is less, it's going to accelerate a whole lot more, thus it dies. Now I have one quick demo for you. I won't run over. Here's a fan cart. It blows air this way. So when I turn it on, will it move? Who thinks yes? Who thinks no? It depends on friction, right? It is on wheels. It's free to roll. If it moves, which way will it move? Point. That way. Okay, let's see. Yay! Can even do it here. And it accelerates because there's a constant force of thrust. So yeah, this pushes on the air. The air pushes back on the cart and makes it move. So now, let's give it a sail. If I blow into the sail in that direction, what do you think will happen? Air on the sail makes the cart move. What's the sail do? Pushes back on that air to slow it down and stop the air. So now what will happen if I turn the cart on? We'll have the propeller blowing air that way and the air pushing on the cart. And we'll have that air running into the sail pushing that way and the sail pushing back on the air. What do you think will happen? One vote for staying still. Any other takers? Who thinks it'll go this way? Who thinks it'll go that way? Who thinks it'll explode? So, quick explanation and I'm done. What are the forces on the cart? There's only two. The fan pushes on the air. That does something with the air. The air pushes back on the cart. There's one. One force that way. Well, those are equal and opposite pairs, right? Air, cart. The air runs into the sail and pushes the cart that way with the same force. So yeah, the two forces cancel each other out and it doesn't move. See you Wednesday.